Hi all, I am B Padmanabhan, Assistant Professor, Department of EEE, Satyabama Institute of Science and Technology, deemed to be University, Chennai. Today in my lecture, I am about to give you a small overview of Electrical Engineering Lab. As when taking the circuit branches, each and every students are facing the situation to meet electrical machines lab. So in that regard, students are facing the problem of understanding the circuits. That is a major thing they are facing trouble with. Doing the experiment they can easily done, but remembering the circuit is very big task for them to overcome this lab. So here I take a platform of giving you the explanation of how to remember the circuits of different experiments. Okay, so in that way I am starting with Electrical Engineering Lab and overview. So while taking with Electrical Engineering Lab, the lab experiments are furthermore classified into two types, AC experiments and DC experiments. So in my first session I am going to deal with the DC machines. Okay, so coming to DC machines, how the machines were classified. So what are the things we are already aware of is DC machines are classified as generator as well as motor, right? So when coming to the DC machines are furthermore classified into generator experiment as well as motor experiment. And there are major classification of DC machines. So DC machines are classified into three types. What are all they? Series, shunt, and finally compound. So DC machines are mainly classified into three types, series, shunt and compound, and coming to the machine side, generator and motor. So here in my lecture I am going to give you the sample experimentation to remember the circuit of 6 different experiments. Okay, so among the 6 experiments, 3 experiments I am going to concentrate on generator side and another 3 on your motor side. Okay, so while taking with generator side, what are the types of generator? As I told you before, series, shunt and compound. So most important generators which we are handling in our lab is shunt as well as compound. The shunt and the compound, both the experiments we can able to do, or the classification of generator can be done in 2 ways. What are the things means in generator, shunt and compound? When you take in your shunt, it is furthermore classified into 2 types. What are all they? Self-excited and separately excited. Compound generator obviously we will be taking self, right? So these are the 3 things which we are going to discuss today. Okay, when taking separately excited, what is that excitation, why it is to be taken separately, that is what we are going to discuss. So the first topic what we are going to discuss is separately excited DC shunt generator. So why particularly in DC shunt generator we are taking this word separately, that we are supposed to remember first. Because in order to remember the diagram, first you want to know the classification, how it was furthermore classified, and how to remember that you want to know. Okay, so in that, first separately excited, the word excited, that means it is giving you the term the excitation of magnetic field. As you are aware of, in any generator we can take 2 parts in the generator. So one is the static part, another one is the rotating part. Static part is nothing but magnetic field and the rotating part is nothing but the armature. Okay, so armature remains same in all the experiments. We don't want to bother about armature, but when we are taking the excitation, that can be done in 2 ways. One is separately excited, another one is self-excited. When we are taking separately excited, nothing but the magnetic field of the generator should be provided with an additional DC supply. If it was self-excited, the generated EMF of the generator itself is going to satisfy the supply for the magnetic field. So that is why it is called as self-excited, and this experiment was named as separately excited. So I hope you understand that what is the term refers to separately excited. Okay, so when coming to the machine, so I am just going directly with the diagrammatic point. Okay, so I am not going to draw the entire diagram as of one, I am going to explain you by steps. Okay, so first you want to remember this is the armature of generator. Okay, can be named as A1 as well as A2. So any generator needs a prime mover to make the generator work. So I will make a motor to be drawn, both were DC, I am denoting it with similarly a motor with armature. So what we did, both were coupled. These both were armature of generator and motor. As any machine which has the armature needs a field for its operation. If it was a motor, the field is required for the running of the motor at its rated speed, and if it is a generator, the field is required to make the generation to be done with the rated. Okay, so I am making a field to be done, right. since the experiment is DC shunt, especially separately excited, so I am not about to connect a field in parallel to the generator directly. So what I am supposed to do is I want to make an external DC field. Okay, that is the difference. Actually, if it was a self-excited, I can able to connect the field directly to your armature of the generator. But here it is separately, so I am making the field supply to be separated, right? So as I mentioned, it is a separately excited, so I am giving it with separate DC supply. Plus minus 220 volt DC. Okay, similarly, the motor also needs 220 volt DC for its running. Now coming to the point, by this the experiment part is over. Actually, by doing this, the motor will work and the generator will generate EMF. But coming to the experimentation point, our aim is not to make the motor to run and the generator to generate EMF. Our aim is to test the performance of the machine. So the performance of the machine can be tested in steps. So the variation in steps can be achieved by making small alteration with your diagram. So how the diagrammatic alteration can be done, that is what we are going to do now. Okay. So the first thing, the motor should be run at its rated speed. In order to do that, we need a rheostat here. So we need a rheostat to make the field of your motor to be get adjusted. By doing that, what happens? The speed of the machine will be altered. So by altering that, we have the chance of making the speed to be at rated. That means the rated speed of your DC machine is 1500. We can able to make it to 1500. So meanwhile, in your generator also, the field should be adjusted to vary your generation. So I am going to add one rheostat across the field supply. So the variation in field can be done by means of taking this. Okay, so I just denoting it with F1, F2, here also F1, F2. Maybe while doing the experiment, the most serious confusion what we have observed is 2A1, A1 and 2A2, similarly 2F1 and 2F2. We are supposed to identify which is your generator part, which is your motor part, and should be made the connection as clear as possible, so that there won't be any confusion while conducting the experiment. Okay, so two things we have done. One is the alteration in your field of motor, alteration in your field of generator, both has been achieved, right? So two other things, maybe on seeing the diagrams or in my lab, whatever the experiment we are doing is looking different, but what you have drawn is different. Actually, what is the change I have done here, or what is the missing part means, in your lab when you are doing the experiment, you have the chances of having a DPST switch, starter and the meters. Those three things I have missed. I'll complete that. Actually, this is the introduction part, whatever is needed for a machine, and thereafter what is the additional things we are using to conduct the experiment, that I will be showing you, right? So rheostat and field, everything is ready. I just complete the values of rheostat as well. 270 ohm, 1.2 amps and minimum. The word minimum for your motor rheostat is quite common in all your experiments. So any motor field rheostat should be always in minimum. You have that idea, not only applicable for this experiment, any experiment if you take, the motor rheostat should be always minimum. If you take this one, 300 ohm, 2 amps, this is maximum position, but this rheostat is particularly called as zero output voltage rheostat. So its connection resembles zero output voltage rheostat. Okay, so two rheostat we have made, two field is ready, the motor is ready, generator is ready, everything is ready. Let me about to complete the experiment by means of the additional terms. As we know that any motor, that too in DC motor, it needs a necessary starter. I am going to add up a starter. So before starting with the starter, I just tell you what are the things. This is nothing but input line. I just name it L, and this is nothing but field. I name it F, and this is armature. I name it A. So by this we can easily identify L, F, A. As we know, the 3-point starter has 3 terminals. F, L and A. This is nothing but 3-point starter. One part is over. And similarly, we need a switch, that is nothing but DPST switch, that can also be done here by means of an arc. Any DPST has a fuse. So a motor always consumes the current more than 10. So obviously, always you can make the current of the fuse of the DPST should be 20 amp for your motor. Any field DPST will be taking only less than 5, so 5 ampere fuse is enough. So here also the DPST switch is needed. I am making a DPST, and a fuse is also needed. This carries 5 ampere current. So the connection part, everything is over, but finally one term is missing. What is that? The tabulation. What is the reading we are going to take? The reading should be done only then if we have meters. The most important point where the student used to confuse is, where should I connect the meter? What is the range of meter I should choose? These are the two things where the students mainly struggling of. So here we are going to see what is the experiment name itself, DC shunt generator. There is no part of measuring any value of your motor. So no need to connect any meters on your motor side. On your generator side we need to connect. This experiment is separately excited DC shunt generator, open circuit characteristics. Open circuit characteristics, the generator itself is open. We are going to measure the EMF induced in your generator. So that can be done by means of connecting a voltmeter here. What is the range of the voltmeter we can choose? Nothing but your rated voltage. The rated voltage of your generator is 220. So almost more than the 220 we are supposed to choose the meter range. So let me take 0 to 300 volt. The type is MC. MC is nothing but moving coil type meter. So two types of meters were available. One is moving coil type, moving iron type. Always the DC meters will be preferring with moving coil type. And any other meters required? Yeah, one more meter needed. Nothing but as we have measured the voltage of your generator. Meanwhile, what is the current supplied to your field will also to be measured. So that can be measured by means of adding a ammeter in series to your field. Okay, so we are supposed to connect the voltmeter in parallel to your armature, and ammeter should be connected in series to your field. So what is the range we can choose? 0 to 2 ammeter is more than enough. Always your field current will be less than 2. Okay, so take it in point. You can have 0 to 2 ammeter with MC. Right? I hope this diagram, what we flow in the flow, what we have done, the diagram is very easy for your understanding. And with this diagram representation, we can do the other experiment as well. Okay, so coming to the tableau column, while drawing the diagram, the part is over. After the diagram, how the tableau column should be done, that is also a huge task. Whatever the meters we have, without any hesitation, you make a tableau column. Thereafter, whether it is needed or not, that we can go later. If there is a meter, that reading should be recorded without any delay. So once if it is recorded, for your calculation, if it is needed, you can take it granted, or otherwise you leave it, no problem. So two meters were available here. One is nothing but your field current. Another is nothing but generator voltage. With this two, we are going to frame the reading. So how to take the reading? By varying your ammeter value, by adjusting your rheostat, your voltmeter values will be altered. So each values of your ammeter value, the voltmeter range should be recorded. Finally, it should be plotted in the form of graph. So while drawing the graph, two graphs is needed, two plots in a single graph is needed, IF across E naught. So in which this IF and E naught should be recorded as a curve. There is a small delay, it should not take 0 directly. That delay is nothing but residual voltage. Any machine has its residual magnetism present inside the machine, that will be created or it will be transferred in terms of residual voltage. Okay, that residual voltage after your value starts, and it seems to be a OCC curve. This is nothing but OCC curve. Right? So we are supposed to draw a slope line. This line is nothing but RC line. Okay, so similarly here we have the field and current. So in order to find your RF line, this is nothing but RF line which we are going to record. Okay, so this both line should meet at a point. This is nothing but RF line, RC line, RF line, OCC line. Here we want to take two things. We are supposed to take a point that should be projected down. This point is nothing but A, this point where it meets is B, and this point is C. Okay, A, B, C. Why I have pointed A, B, C means in order to find critical speed, N critical. N critical is nothing but BC divided by AC into N rated. BC divided by AC into N rated. N rated is nothing but 1500. BC is nothing but the value of your scale. What is the value recorded according to your voltage? That should be made here, divided by AC, together gives your critical speed. And also you are supposed to find critical resistance RC. To find that, we have a slope line in which you just take a triangular representation of slope. So del E divided by del I, that gives your RC. By that your experimentation part is over. So second experiment what we are about to deal with is load test on self-excited DC shunt generator. So what is the difference we can easily identify in your previous experiment is separately excited. That means the excitation is given separately, separate DC supply is provided for your field excitation. But for this experiment, so excitation itself is provided by your generator itself. So that is why it is named as self-excited of the generator. Okay. So that to the machine what we are going to take here is DC shunt generator. So self-excitation in the sense, as you know that what is shunt generator, nothing but parallelly connected field to your armature. So armature is actually the diagram I have not rubbed entirely. Your motor connection is what we discussed earlier, the same has been available here. Only on your generator side, in the previous case I have drawn the field separately. This case how the field can be taken into account, that's what we are going to learn, right? So any shunt motor needs a parallel field. The same way the generator also needs a parallel field. I am just ending with the parallel field, right? But as I told you before, in order to make the speed to be get adjusted, we need a rheostat to adjust the field current of motor. Same way, in order to adjust the generation of your generator, we need a rheostat on your generator side. So I am going to add up one more rheostat here. So one common difference you can observe that motor's field rheostat to be minimum, but in generator the field rheostat should be maximum. So by this point you can clearly remember that any case the motor rheostat should be always in minimum state, generator rheostat should be always in maximum state. These are the 2 points which you want to remember for all the cases, not only for this experiment, for all the experiments. So the range you can easily made, as we for the previous experiment you can know. But for the previous experiment we have 0 output voltage rheostat, but here just the maximum pointed rheostat is enough, right? Okay, this is what the construction point of or the systematic arrangement of your experiment. But there is some point named load test. We are going to test the generator according to the variation in the load. So we are supposed to add the load also. So this much diagram we can remember from your previous experiment itself. But when going for the load, that is something in addition. Just we are going to remember. I am going to connect a load. That too not a static one, I am going to connect a variable load. Right? By means of connecting this, what happens? As per our aim is achieved, load test. So I have connected a load. But when the load is directly connected to your generator, when we are turning on the switch of your motor and the motor is started and the generator also generates EMF, load is already connected means we can't able to make the generation to pick up. The generator will hang up. So we are supposed to make, there is a separation until the generator reaches its maximum rated value, we are not supposed to turn on the load. So that should be done by means of the separation to be achieved with a switch. Clear? So I have added a switch, nothing but DPST, as how we did for motor, the same. Also it needs a fuse. So generator's voltage and the current will be, load current will be more than 10, so we have it as 20 amps, right? So field F1 and F2. Now the connection part and everything is over. Now coming to the recording part. So recording in the sense load test. We are going to check the performance of generator according to the variable load. So that should be recorded with different readings. So whatever the readings required, any meters to be connected across motor, if you think about, no need. Why? Because the motor is needed only for giving the prime mover input. That means the mechanical energy alone the motor is about to provide. No electrical changes on your machine of motor should be recorded. So we can leave this part. When coming to this part, what are the points to be get recorded that you want to remember? First thing is we have a load. How much current consumed by the load, that you want to remember. So we can have a ammeter across your load. So ammeter is 0 to 20 amps MC. Similarly, field current, how much field current consumed to make your generation to be achieved. For that you can add one ammeter here. This is 0 to 2 amps MC. From the previous case, I hope you remember, field current should be always less than 2, so we can add 0 to 2 ammeter. And the generation voltage we are supposed to record, that we have a voltmeter here. So rated voltage of generator is 220, so we want to make the meter more than that. So I have add 0 to 300 volt MC, right? By this your diagrammatic part is over. Now coming to the recording part, as I told you in the previous case that any meters available in your circuit, directly you can take it granted for your recording purpose. How many meters available here? 3 meters. One is voltmeter, another one is ammeter, nothing but IF, and the second one is load ammeter, nothing but IL. So 3 things we can take it granted for recording: E, IL and IF. 3 things we can take it. Okay, and finally we are going for reading purpose. That means the calculation part. While taking the calculation part, what is the thing we are going to do is final estimation or the final justification how we are going to provide is what is the characteristics which present inside the generator and what is the characteristics which present outside that means on the load side. So inside the generator we can take it granted as internal characteristics, and outside the generator on the load side we can take it granted as external characteristics. So what is the curve? What we learned in the previous experiment? Nothing but magnetizing characteristics, because in that experiment according to your field how much voltage is generated, that we have taken as magnetizing characteristics. Here internal and external characteristics. So as I told you, internal means inside the generator. Inside the generator means generated EMF EG and your current IA. So IA and EG together gives internal characteristics. EG versus IA. So here in x-axis we can take I, y-axis we can take V. So external characteristics what you are going to take is VT and IL. That means your load side, the load voltage and your load voltage and your load current, IL and IG. Sorry, IL and VL. So that can be taken as external characteristics, VL versus IL. On your graph we can easily understand that the curve has a minimum deviation from your internal and external. The top one is your internal and the bottom one is your external. Always due to certain drop the generated EMF may not satisfy your load directly. There might be certain resistance present inside the generator that creates a voltage drop. On satisfying that, the remaining voltage will be taken to your load. So that is the reason the deviation in your curve achieved. So one is your internal, another one is your external. So next experiment what we are going to discuss is DC compound generator. As I told you in the initial case, two types of generator we are going to discuss here. One is shunt, another one is compound. So the previous diagram I have not rubbed anything, just the same diagram is available in your book. But what is the change you want to remember? Because people were considering that two different experiments. It's not like that. The experiment point, conduction point, connection point, everything remains same. What is the minor change which makes your experiment to be get changed? That we are going to analyze here. Okay, so only inside the machine what is the type of connection going to vary, that is to be recorded in your diagram. As we know that compound generator has both series and shunt field winding. So for the field granted in your shunt is only your F1, F2. But when taking compound the same as your F1, F2 followed by your series field winding. So as you know that series field should be connected in series to your armature, right? So I am going to connect series field I have made. So whose name is S1 and S2. Since the series field should be named as S1 and S2. In compound generator there are two methods to conduct the experiment. One is differentially compounded, another one is cumulatively compounded. So the diagram what I made is for cumulatively compounded. So what is the difference in identifying the difference between the cumulative and differential means? As we know that we have poles in your generator with pole shoes. Okay, so in pole, take for example, I am going to wind the parallel field winding first, F1, F2. I am also going to make the series field winding. Since it is a compound, both will be available, S1, S2. So if I am taking granted in means of taking cumulative, that means cumulative, summing up the magnetic flux produced in your pole. So I am going to take the current direction of your field F1 and S1 to be in a same direction to make a cumulative flux phi 1 plus phi 2. On the other means, if I am going to take differentially compounded, on that case I am just going to interchange this S1 and S2. That means I am going to reverse it, S2 and S1. So obviously what happens, the current flows in your S1 S2 coil will be get reversed. By means of reversing that, the summation of flux which happens in the previous case will be converted to the difference of your flux. So that is the reason which makes your generation of your compound generator to get varied. By means of the variable connection, the generation should also be varied. But coming to the recording part, the calculation or the tableau column, everything remains same. So what are the columns readings to be noted? First one is terminal voltage V, followed by IL, IF, and then IA and E. E is nothing but V plus IA RA. By means of doing this, E is recorded, V is recorded, IL, IA, everything has been recorded. So with these readings and the calculation what we have observed, we are going for the graph. So graph in the sense the same, because we have not altered anything. Our aim is to check the performance of performance of generator according to your load. So the load remains same, the the meters and everything remains same. Only the inside connection of your generator is going to vary. The previous case there is no series field winding. For this case we have the series field winding. We have added with S1, S2. Obviously your connection and the graph everything remains same. Okay students, so far we have discussed about the generators, different types of generators in which we are using in our lab for the experimentation purpose, and I hope you remember whatever the types you have learned. Can we have a revision? Like shunt generator, in shunt separately and self both we have discussed, and the compound generator. 3 different experiments, and the experimentation point and the recording of reading and the graphical part we have discussed with. So with this I am going to end this session. In our forthcoming session we are going to discuss about the various types of DC motor which we are going to use in our lab and its characteristics and other things. Thank you.